Well, it's about time. We'll get started. Hey, I want to thank everybody for coming. I appreciate your time. And this is Introduction to NATS. My name's Colin Sullivan. I'm product manager of NATS. And we actually have Derek here who can answer questions after the presentation. Derek's a creator of NATS. So let's get started. So what is messaging? Just to start at a higher level, messaging is message-oriented middleware, which is software or hardware that's it's an infrastructure that supports sending and receiving messages between distributed systems. Or, as some have described it, it's the intersection of the stuff that network engineers don't want to do with the stuff that application developers don't want to do. Why do we need messaging? Well, developing and deploying applications in distributed systems, it's really hard. It is. Very complex. Message-oriented middleware vendors provide a set of basic features to make this easier. And these can include multiple message patterns bundled in one tech, location transparency, and the decoupling of data producers and consumers. This means I don't need to know exactly where the application that's sending me data is. I don't even need to know what that application is, and vice versa. I don't need to know where I'm sending the data or who's going to consume it. In fact, I should never even assume who's going to consume the data. And built-in load balancing. So messaging systems have been really successful over the last 30 years in providing features like these. Some messaging systems have a subset of these features, some have all of them. But messaging has been designed to meet the needs of the day. It was originally developed for static systems where you knew exactly what was running where. Software ran on servers with long-lived addresses. Configuring endpoints was onerous and infrequent, and that's because scaling required manual positioning of hardware and software. You had to go put a machine in a server room. That also meant deployments were smaller and systems were siloed. These static systems were very predictable, and that allowed resiliency to be built by shoring up the weak parts of the system, but with an emphasis on individual servers and individual clients. Most messaging products today carry this legacy. But things have changed. Technology's matured. These old monolithic apps that you have had been decomposed into microservices. Lightweight communications are needed now for microservices, edge, and endpoint devices. We need a resiliency with an emphasis on the health of the system as a whole, not individual components. We need ease of use and ease of deployment for CI/CD. We need really, really easy and low-touch operations. We need to be highly scalable with built-in load balancing and very little configuration. And we need identity and security that's consistent end-to-end, from edge devices to back-end services. NATS was created specifically to meet these needs. So what is NATS? NATS is an 8-year-old production-proven cloud-native messaging system. NATS was designed to be easy. It's for developers and operators that just want to spend their time doing their jobs. They don't want to spend their time having to learn about messaging or manage messaging. So the DNA of NATS is simplicity, performance, security, and availability. It was built from the ground up to be cloud native. NATS supports multiple qualities of service, at least once and at most once messaging. Support for multiple communication patterns, and we've got over 30 client languages. NATS was created by Derek Hollis, and Derek's been solving these hard problems in distributed computing for over 25 years. He was SVP and Chief Architect at TIBCO, a technical director at Google. Derek architected Cloud Foundry. That was actually where NATS was born. He was CTO and Chief Architect of VMware, founder and CEO of Apcera, and currently founder and CEO at Synadia. Derek has built a highly experienced messaging team around NATS. We've got over 100 years experience specific to messaging. And we have a very engaged user community. I was really surprised to discover this when I looked on DevStats for CNCF, that over the last 8 years, we've had over 1,000 different contributors. And there's over 100 with more than 10 commits. We've got over 30 public repos. We're getting close to 36 million NAT server Docker Hub pulls and 25 million NAT streaming server pulls. I'm really hoping after KubeCon, we'll break 1,000 NAT or Slack members, and we've got a really good cadence of about 5 releases a year of the NAT server. Many users and adopters, large and small, from many different verticals. So NAT solves a variety of different problems. NATS is used in cloud messaging as a microservices transport or control plane for service discovery and event sourcing. We also find NATS being used in IoT and edge, mobile and big data. NATS is used for high fan-out messaging. And we're finding that people want to augment or replace their legacy messaging with NATS. We get a lot of requests for bridging to other technologies. We have a really great integration with Kubernetes through our NATS operator. The NATS operator will be installed and it automatically creates network services, automatically clusters NATS servers, which isn't hard to do to begin with, but it does a lot of other things as well. It's got authorization with service accounts, so you can tie into Kubernetes authorization. Any sort of configuration is stored as secrets, and anytime you update the configuration, the NATS operator will reload the NATS servers for you. It's a hot reload. Nothing has to go down and come back up. And then we also have a NATS streaming operator, which clusters NATS streaming servers together if you choose to operate them that way. We've got a Prometheus NATS exporter. We've got plugins for FluentD and help charts. Let's talk a little bit about messaging patterns, where we've got publish subscribe, load balance queue subscribers, and request reply. But before we understand these messaging patterns, we need to understand what subjects are. A subject is simple. It's a string that represents interest in data. So a simple subject's foo. If I publish a message on foo, any subscriber who says, I'm going to subscribe to foo, will receive that data. It can be hierarchically tokenized, where you can string tokens together in a subject, and that allows you to create wildcard subscriptions, where the star operator in a subscription will match a particular token, or greater than will match any token and anything beyond. So for example, foo.star will match foo.bar and foo.baz. Foo.star.bar will match foo.something.bar, and foo.bar matches any of the above. And you can even just say, I want to subscribe to absolutely everything going on in NATS. And if you have authorization to do so, you can do it. So with the publish subscribe pattern, you publish a message to a subject, and 1 to n subscribers, however many you have, will receive that message. This is used for high fan out. It's used for specialization or parallelization of work. So for example, you might have one subscriber that updates a log, another one that will, upon receiving the same message, will update a UI, and a third one, let's say it's sensor data, might trigger an alert of some sort. And then we take that and we tweak it a little, and we've got a load balance queue pattern. So when you create subscribers, you can optionally add them to a group. And when a message is published to these subscribers, one of that group will receive it. And this happens randomly in core NATS. NATS streaming uses a little bit of intelligence in which message it sends it to. But this is used for load balancing, auto scaling, and lame duck mode. So in the diagram, you can see the publisher publishes messages 1, 2, and 3, and these will be spread out amongst subscribers. We also have a request reply API, and those are available to most clients. But because under the hood, everything in NATS is a subject, when we do request reply, it operates over unique subjects, but that lets us use some of these optimizations to build some really interesting request reply patterns. So you can request reply to many, and you can tell the NATS server, I only want one response. The first response that comes in will be handled and passed back to the client, and the NATS server will unsubscribe, circuit breaking, preventing that message from propagating any further. That gets you the lowest latency response. You can respond with queue subscribers to load balance. So if my replier to my message, my replying application, isn't performing and isn't giving me the response times I need, all I have to do is scale. All I have to do is launch another instance of this. It'll subscribe. It'll let the NATS server know it's part of this group and start receiving messages. What's really important here is there's no config changes. This is automatic. You just launch another instance. And supported clients also provide a drain API. And this allows you to do graceful shutdown to eliminate any sort of data loss. It's great for downward scaling and great for upgrades. So you've got your load balance queue subscribers, and instead of just closing your connection, you drain. And drain unsubscribes, processes the rest of the messages, and then closes your connection, allowing for a graceful shutdown. NATS performs extremely well. We're upwards around 20 million messages a second with one server, one stream, and upwards of 80 million with multiple streams. And this is in core NATS. This is extremely fast. We get there by being smart in what decisions we make in the design decisions. So we design for scale. Anytime we're looking at making a change, say what happens if we multiply this by a million? And also we take a very careful analysis of the fast path. So as we watch how messages will flow through the server, say, are we adding a lock? Are there going to be additional mem copies? And then we also performance test every change to make sure we maintain this speed. But just as important as these decisions to make things fast are what we've decided not to implement. And people have asked for these. You feel kind of bad saying no, but it's not part of core NATS. It's not part of our tenants. So we don't have any message guarantees in core NATS. We don't support transactions. We don't support message schemas, things like last will and testament or JMS message groups, because that doesn't fit into the performance characteristics. These are things that can happen outside of NATS in your application or at a higher level in NATS streaming. NATS is really lightweight and scalable. We've had one user, actually R.I. Paneer, actually he's a maintainer now. He's joined us. And it took him 90 seconds to pull 50,000 nodes with NATS and get responses back. We worked with him and we got that down to 1.8 seconds to pull 50,000 nodes and get all the responses back. I'm sorry?
I think it's lower now.
Oh, yeah, it's under a second now. And NATS prioritizes the health and availability of the system as a whole over any individual client or server. And I call this selfish optimization. So when a client is not consuming fast enough, a core NATS client, the NATS server will actually cut that client off. Because in the cloud, what do you want? You don't want to service an unhealthy client. You want to cut it off, have an operator take a look at it. Maybe it's restarted. We have full mesh clustering of NATS servers, which means any server can go down and the rest just take over. Clients will automatically fail over to new servers. And servers and clients, their connections self-heal in that they try to recreate the connections to existing servers or even new servers they might have discovered. NATS is extremely resilient. This simplicity allows us to be very, very resilient at scale. Even though we plan for the worst, we have users that run NATS for months and months and months upon time at a time without running into any issues. NATS is simple. It's a single binary with about under 10 megabit Docker image, no external dependencies. We have a text-based protocol with just a handful of verbs. And just to clarify, while the protocol itself is text-based, it's really simple. So you've got pub, sub, message, connect, info. The payloads are binary. And what this allows you to do is send a message of any sort of type, but with the text-based protocol, it makes it extremely easy to develop clients. That's why we have over 30. We've got a lot of contributions in clients. I mean, someone just started a Dart client for us. It's very, very low config. So clients only need a URL and credentials. Servers will auto-discover. And you can share your configuration files amongst servers in a cluster so that you've got one source of truth for things like authorization or policy. And a very, very simple, straightforward API. I mentioned auto-discovery a bit earlier. So auto-discovery is where the NATS servers will detect topology changes and share this with each other. So let's say you have a cluster of 3 servers and you want to scale up. You add another server, you direct it to any one of those 3 running servers. They all exchange information about each other, and suddenly you've got a full mesh with 4. You've got 4 in your cluster. This happens transparently to clients. They don't have to have any configuration updates. This actually happens transparently to servers. They don't need any configuration updates as well. But there's more. So this topology information is also passed to the clients. That means the clients can then connect to servers they were never originally configured with. Now, imagine this in a situation with a rolling upgrade, or you want to move regions. You can simply launch new servers, build your cluster across regions, and drop your old servers, and the clients just simply reconnect to the new cluster. They don't even really notice a difference. we've got a very, very simple API where we connect, we publish, send a series of bytes, flush, and the flush is just, in this example, just to show that you can flush a message to get lower latency. And here's the Java API that would receive this message. So you subscribe on DemoNet simple subject, just print out a message after you create a connection. That's it. NAT supports 2 different delivery modes. So I've been speaking a lot about Core NATs, which is the basic installation of NATs. That provides at most once delivery. So there's no guarantee. Messages can be lost. Applications have to detect and handle messages. Sounds fragile? It's really not. It's how the internet works today. But then some people need more. On top of that, we provide at least once delivery, which is NAT streaming, where a message will always be delivered, and in certain cases, it'll be delivered more than once. Generally, I mean, those are always failure cases. There is another delivery mode that we've chosen not to support, which is exactly once. We'll argue it's unnecessary, it's always complex, and inevitably slow. It essentially becomes like a distributed transaction. And Derek always loves to discuss exactly once. So with NAT streaming is a data streaming system that sits on top of NATs. It provides at least once delivery. You can replay messages, so you can replay the last hour's worth of data that's been received. Or give me everything since sequence number 10,000. It can also provide a last value cache. An application comes up, hey, I just want the last message that was sent. You have durable subscribers, where subscribers are receiving a stream of data. If anything bad happens, whenever things return back to normal, you'll just pick up right where you left off. We've got rate matching per subscriber, different types of storage, including memory, file, and database. We've got a couple different ways to configure fault tolerance through full clustering or a fault-tolerant configuration, and you can scale through partitioning. Now we're going to talk about some of the newer features with NATs. Global deployments. So this is new. Actually, the changes here are in master branch right now. We'll be cutting a release pretty soon. So we've got super clusters. Imagine clusters of NATs. It uses a spline-based technology. We use optimistic sends and interest graph pruning, and also provide intelligent support for geo-distributed queue describers. That's actually really interesting. So remember I was talking about the queue subscribers, where you send a message and it'll randomly send to one of the subscribers to load balance? Well, it can be smart geographically. So if I have a queue subscriber in Japan, one here in Seattle, and I'm publishing from Seattle, it'll use the queue subscriber in Seattle until it's gone. And then it'll back up and use the one in Japan. We've also introduced accounts. So accounts are isolated communication contexts. They allow multi-tenancy. So what this does is this bifurcates technology from business-driven use cases. People used to silo data because of software and hardware limitations. This is no longer the case. You can silo data if you want geographically, or you can silo data with accounts horizontally across the global deployment. It's easy, secure, and cost-effective because one NATS deployment, there's one NATS deployment for operators to manage. And it's decentralized. So we've built accounts to be decentralized so different account administrators can self-manage. And I'll talk a little bit more about that, but you can share data between accounts with secure streams and services, and only mutual agreement between these accounts will allow this data to flow. So services are a secure RPC endpoint. RPC, again, or request reply, is that one-on-one conversation, a phone call. And you can have two accounts. One will open up a service, the other one will import the service, and then they can talk. You have streams as well, which instead of a request reply pattern, that's your publish pattern. That's publish subscribe. So the stream of data can flow through. But what's really, really cool about this is within an account, the subject namespace is isolated. So if I have two applications in account A that are publishing on Foo, no subscriber in account B will receive Foo unless you create a stream to allow that to flow through. All this is transparent to clients. There's no client configuration or client API changes to get this. NATS is secure. We have authentication, encryption. You can set some policy, and we've got subject-based authorization. You can update these in the server anytime with a hot reload, and clients don't really notice a difference unless they're affected by the policy change. We support TLS with CA certificate support, client certificate support. TLS 1.3 is coming soon. We have N keys that you can use as identities. These are ED 25519 keys that we've made very easy. They serve as identities in the NATS server, and we'll continue to support user password. You can decrypt passwords in storage, so should an administrator look at a config file, they still won't know what the password is. So N keys are a new NATS identity and authentication and authorization system, or actually just an authentication system, but they can be used with authorization. So again, they're ED 25519 keys. They're very fast and resistant to side channel attacks. You can sign and verify with these, which allows a new form of authentication where a client connects to the server sends a nonce back, which is just random bytes that are salted, and then the client signs that with his private key, sends that back to the server, and the server checks to make sure that the client is who they say they are. And what this does is this allows the NATS server to operate and never have to maintain private keys, only the public keys of the client. You can encapsulate these in JWTs that will associate users and accounts and permission sets with this N key identity. We support encryption. You encrypt through TLS. We default to the most secure cipher suites. You can override encryption to define a list of ciphers, elliptical curves. And NATS streaming in Q1 is going to support encrypting data on disk. We have subject-based authorization, which is who can control, you can control who can publish and who can subscribe to different subjects. And you can use wildcard support. And we also have allow or deny clauses, which provides a lot of flexibility. You can actually generate some pretty complex authorization scenarios with very terse configuration this way. Like everything else in NATS, we go for simplicity. Monitoring is very, very simple. Each server is monitored independently. It returns JSON. And the simplicity allows you to build really complex tools on top of it. We've got integration with Prometheus that allows aggregating and alerting on NATS for various server events, where Prometheus, we've got a Prometheus exporter that just takes this JSON and serves it up in a way that Prometheus likes. We also have a NATS top tool that was written by Wally right here in the audience, which is a really, really handy tool that takes this JSON, presents it in a way that's very familiar to Linux users. In production monitoring, we advocate that you use the Prometheus exporter and Prometheus server to generate alerts. And then you can put a dashboard in front of it. And this is what one looks like. So we'll go run through some upcoming features. We get a lot of requests for other messaging product integrations. So we're looking at integrating with MQ series, but then we're also looking at integrating with Kafka. We've got data at rest encryption and streaming. We've got we call it Project Jetstream. It's NATS streaming version 2.0. It's going to bring a more tightly integrated streaming solution to NATS and some really cool features. MQTT is ubiquitous. I mean, NATS is a great use case for IoT, being as lightweight and performant as it is. And we are going to support MQTT natively. We're going to add WebSocket support, and we're going to develop some microcontroller clients. We welcome contributions of all kinds. Some ways to contribute are blogs. You can fix a bug. If you find anything in our documentation, please let us know and even submit a PR for us. You can propose features or present your NATS project at meetups. If you do, let us know. We'll send you swag. So let's do a quick demo. Whoops. And I've actually had this demo running. So remember, I was talking about the queue subscribers and request reply. So I've got this set up So I have a requester. Let's start with a requester. I have a requester that's Prometheus enabled, and all it does is it connects to NATS. It starts up, in this case, 50 simultaneous requests that it's trying to pound on a replier, and it sends this request and just records how long it takes. I have a replier that connects to NATS, and it simply queue subscribes, and then sleeps for a period of time, simulating a 50 millisecond workload. I've had this running in Kubernetes with the NATS operator, and let me refresh this. I've had this in Kubernetes with the NATS operator. So here's the NATS operator. We've got Grafana and Prometheus just so I can visually show you what's going on. And we've got a requester and one replier right now. If we look at our statistics, this is what is being returned. You can see we're handling about 20 requests per second. We're averaging, we're getting about 2.5 second average response time, which is about right, 50 milliseconds by 50 requests at the same time. And you can see pretty steady with latency between 2 and 4 seconds. So what we're going to do is, without any config changes, we're going to scale the replier. So we scale the replier up. Now, if you remember when I was talking before, what we've done is just launched 9 more instances of this replier. So now when the requester is sending its requests in, the server's randomly sending these requests to repliers. So if we look at what's happening, your requests per second just jumped up. It's getting close to 200 now. Your average response time has plummeted. And you can see with the latency histogram here, you're now in the 128 to 256 millisecond response time, even down as low as 32 milliseconds in some cases. On average, these are some of the off hits. And all this was done with a very, very simple queue subscriber and a click of a button to scale. So that's the presentation for today. Any questions? And Derek, you're welcome to come up and field any questions if you'd like.
Sure. There were two things I hadn't heard before. Named up and nice will.
Yeah, so Maxwell investment is something that MQTT popularized, which says when you start up and form a connection, you can unconnect. You can tell the server, if I go away, send this message on my behalf saying I went away. Lame duck is something that the first time I heard was when I was at Google, which says instead of just taking a server out, if you know you're going to take it out, kind of give it a signal and say, hey, stop accepting new stuff, but bring everything that you're working on now. And so a lot of these techniques, I think, are extremely effective and keep you at most one's delivery spans. So that fire and forget, that NATS core that's so lightweight. With frame mode, we can run crazy tests where we're auto unsubscribing, killing, and going down and up and everything, and not a single message is ever dropped. And that's not to say that it can't happen if something underneath of us changes, but it makes it extremely resilient, without you doing anything wrong. And we did that so that we can be cycling applications, cycling servers, and things like that without losing messages. Yes.
How do you see Kafka position versus NATS streaming? When would you recommend picking one versus the other?
So the question is Kafka versus NATS streaming. When would I pick one or the other? I actually think it's a good story together. Colin and I have done a couple trips already this year. People who are using Kafka and have large investments. And what happens is whenever you pick a technology and you kind of go all in on it, one of two things happen. And one's a very small percentage, which is everything's great. And the other, which usually happens, is they're like, well, it works really good for this, but then we decided it could solve world hunger, right? And it doesn't work so good over here. So what we were seeing is a lot of people said, we like the concepts of streaming and log replication and replay. We just want to have something that might be lighter weight, easier to operate on the edges. I don't know Kafka extremely well. I understand the design, but when we were setting up the thing for our trip to New York, you know, it was very hard to set up. And I was using even like the document images that were supposed to make it simple. And I've been doing this for like 30 years. I was like, this is really not good. And so, with that being said, we're not going to go in and ever say, oh, rip Kafka out. It's like, no, we can augment. So we put a transparent bridge in, they're going back and forth. And we have some really cool ideas for V2 that we think are going to be really interesting.
Nat streaming V2.
Yeah, sorry.
Can you give us some insight about all the data replication inside of the NATS servers works and how the failover, I assume like origin of the data. For example, one of my NAS server crashed, how does the failover works? How does there's hierarchy of data?
So the question is, what happens inside the server? What happens if it crashes? How do you guarantee no data loss? So NetScore doesn't guarantee no data loss. It's kind of like the internet. You know, if you click on something that doesn't get what you want, you go, click it again. The reality is that the most resilient distributed systems are built on very simple and predictable patterns. Predictable is the most one, but I like simple as well. So in NetScore, if something happens, and by the way, if you get a NAT server that crashes, come to me, I'll sign a $100 bill and give it to you. We haven't had one of those happen. I think you crashed the last time, like, what, 5 years ago? So we try, we're not perfect, but we try so hard to make it so resilient, so lightweight, it self-heals itself, it puts itself back together, it communicates with clients transparently so that they know where to go. Inside the server, the general gist of things is that there's an interest graph propagation. And that's what Colin was alluded to in our supercluster technology. We do some really interesting tricks for global scale. And then the data plane flows in reverse of an interest graph. So I say, hey, I'm interested in food. Well, I'm going to tell you about that. So that if someone sends you a message on food, you go, oh, Derek's interested in that, you send it to me. But again, core NATs, there will be data loss. NAT streaming will persist things, right? Either in memory or on disk or in distributed databases, whatever that is. And so they can recall those. They can send those data at a later date.
Is there any data replication or?
Kafka, as far as I know, what we hear a lot, and what we try very hard not to do is, we're going to make a change on the server, and you're going to have to change all your clients now, whether it's a configuration, an upgrade, or whatever like that. So even with the new technology that Colin was talking about, with what we call NGS, the old client should still work. The code still just does the same thing, sends and receives messages. Now, very intelligent replication, but not on the just Google GFS/R5 or whatever type thing, which is usually kind of wasteful. So we're trying to, and they got much better at it after I left, but we're trying to do some really interesting things there and stay committed to the philosophy that it's just easy. But it does everything predictably, but the things that you're supposed to be doing, like security and things like that. Yes?
So for IoT data, you're usually not interested in all the data. You need some filtering on the data before you get a data replication.
So the question is on IoT, and do you want all of the data? I think that's a great question. I don't know if it's a specific NATS question. What I think it is what type of data are you generating? How big is it? What is the cost to transport it? Let's say, for example, from an endpoint to the cloud versus an edge IoT gateway versus gossiping between themselves. We want NATS to be the enabler of that. So if you notice when Colin was talking, the NATS server already runs on like Raspberry Pis and ARMs and stuff, and we're going to push into microcontrollers, especially for clients. But I think those types of questions are more about how do you design a system, you know, a full end-to-end distributed system to achieve what you want, and we just want to be part of the story. Now, we've all done these systems before, so we have opinions, you know, like if you say, well, I'm talking specifically about this, I'll tell you what I think, could be wrong, and it's free, so you get what you pay for. But Yeah, it's all in the application, and the notion of edge and edge propagation and sensors is changing every day, right? Everything is keep pushing further out. So right now, when I think of very endpoint type things, I'm actually starting to think of extremely restricted communication channels, and probably battery powered, which might not be what you would say was is IoT. I'm saying that a lot of the consumer electronics in your house actually probably are more edge, not necessarily IoT anymore, right? I mean, they're running on processors faster than I went to school with, in the 80s. So, yes.
So it might be a two-part question. Coming from a kind of a Kafka background, there's this, like you said, kind of going all in as kind of a data backbone,
Mhm.
right? The whole distributed database design out for that. Do you see NATS as a good alternative for that? Kafka does something like that.
So the question is, if a company is going all in on, the using things like Kafka and streaming to represent a global state. So, for example, what we always used to put in the database, now people are saying, oh, replay all the messages and the events, and then you come up with the same state. And it was NATS applicable for that. I see sometimes architectures that I kind of go, yeah, that kind of makes sense. I get it. More often than not, I look at it and I go, I just wouldn't do it that way. Not to say that's right or wrong. And we have these conversations all the time, and it's always a transition from development to operations, which sounds like it should make a lot of sense. But what I mean is most of the times when you talk to developers, and we say, oh, we do blah, 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 and they go, why? All I need to do is ask him a question. I just need RPC. Step away. I don't need any of your crazy stuff. But then you get into production, right? And you're going, well, okay. And the golden rule that all of us who have been doing messaging for so long and just learned it's not an IQ thing, it's just a scars on your back thing, is never make an assumption today when you send a message what that message can be used for tomorrow. And so what we see is when you transition to ops, it's like I'm still asking you a question. And I, as a developer, I know I'm asking you a question. But now all of a sudden he's moving. He's coming in and he needs to do compliance. So he needs to see my requests and his answers. And I don't want to change, and he doesn't want to change. Now all of a sudden we need 10 of him. I don't want to be installing load balancers and moving stuff. And now we want to move them to a different cloud, and oh, geez, and everybody's throwing their keyboards. NATS takes care of all of that. So it allows you to transition from a simple request reply RPC model in dev into a production system where you can change that whole system without ever changing him and I. And I like those patterns. And again, the system is extremely predictable. So when you make changes to it, you know exactly what it's going to do. You're not going, hope this works, you know what I mean? Which we've all been there. Now, that being said, we are going to invest a good amount of effort into where we feel we've seen those patterns and they make a lot of sense. And we're trying to take that plus a lot of the feedback that the community gave us on that streaming and roll that into Jetstream. And a lot of the feedback was, it's not, you went too far away from NATS, come back. You know what I mean? We like this, just add us a little bit of at least one semantics, but don't make it a different API or don't make it feel like it's apples and oranges. So,
Sorry.
no worries.
I think it's nice. So with Jetstream and part of the reason that Kafka is a good choice for the side or the ecosystem surrounding it.
Mhm.
Get into Kafka Connect, tools for actually seeing your messages, especially as a dev. Like you said, when you're first getting into it, you're like, what are my messages? What am I actually sending around? How did this happen?
Mhm.
And visualizing it rather than just writing something in the command line, spitting it out and then listening. Is the ecosystem there for NATS? Are they going that way, or is that part of it?
So the question is about Kafka's attractiveness, and if I say it wrong, tell me I'm wrong, but Kafka's attractiveness is that there isn't a massive ecosystem and a massive amount of built-in integrations and connector technologies already. We haven't gone down that path, but our ecosystem has. And all of us on the team lived that in the 90s, where all we did was TIBCO adapters and stuff for like years on end and stuff. So yeah, we're definitely, we're looking at that. We're trying to pick and choose. We got about 1,000 Slack members now, and it feels like a great ecosystem. People are always willing to help each other out. It just feels right. Can it compete with Kafka's ecosystem today? Probably not, but I don't know if I want to. I don't even like Java anymore, so I don't know.
Yes.
So on the whole supercluster feature, Colin gave an example of a subscriber in Seattle and a subscriber in Japan. I think it's on closer. How is locality being represented?
Yeah, so the question is, in superclusters, how is the concept of locality playing a role in the distributed queuing algorithms? So the way it works is clusters today, so if anyone has used NATS, they probably know about the clusters that exist today. Full mesh, one hop. I've always done those. The internet actually is based on those as well, even though they don't scale, so they logically underneath their full mesh, one hop, BGP, and then you try to do weird stuff on top. Our superclusters are the same way. It's essentially clusters of clusters in a full mesh, one hop. So it sounds really, really cool, and it is when you see it working. We have it working in NGS, which is our global system. But what it does is it says, oh, I'm going to pin to my local cluster. And when I send a message, I know if there's any interest locally on a queue group. And so if it's like you're listening on Foo and you're part of BAR, we do that. When we fail and there's nobody home in that local cluster, the supercluster technology that it bifurcates inbound and outbound, it does a spline-based technology so that there's no single point of failure. There's no one blessed guy that's the one sending all the data over. So we think it's kind of cool. But they understand independently all the RTT times to all the other gateways. And so what they do is they have them sorted internally all the time. And so they just say, oh, we're going to send it to him. He's only 3 milliseconds away.
Do they know if the subcluster 3 milliseconds away has got a subscriber that's already listening to that? Or just need to try that and potentially go down the list of subscribers?
Yeah, so the question is, do I know there's a subscriber over there? So this is this could be like a 3-hour conversation, but I'll try to make it really short. In local clusters, small clusters, the ones that exist today, interest propagation always happens. So if he listens to Foo, everyone in the cluster knows he's listening to Foo. Now we've optimized it in the latest version that's on master, such that if there's 1,000 people listening on Foo, it only goes over the wire once saying, hey, someone over there is listening on Foo. So it's gotten better there. That actually doesn't work, though, very well with clusters of clusters and, you know, tens of thousands, hundreds of thousands, millions of accounts, hundreds of millions of users to say, yeah, we want to have every server know everything about the world. So the way, briefly, that the supercluster gateway technology works is that we start in an optimistic way, which is, oh, yeah, I'll send you everything. And then you'll prune the interest graph. And what's nice is that when Colin was talking about accounts, think of accounts as like the containers for your messaging system. They put a little wrapper around it, right? And so you're kind of isolated in there. So if I'm sending something over and he has nobody even at home on that account, he will actually not just prune the subject, he'll prune the whole account. And I'll remember that. I'm like, oh, okay, fine, I won't bother you anymore. And then we have a way that under degenerative cases where and what we're trying to do is minimize the amount of traffic on the wire going back and forth. But there's degenerative cases where the pruning method might actually start generating more traffic than perfect knowledge mode. And so we auto switch to perfect knowledge mode. So he can go, hey, stop sending me all this crap. I will promise you, I'll tell you what I want you to send me. Otherwise, don't send it. And so the system dynamically is switching all the time based on that. So that was a little bit longer answer, but it's cool tech. I think it's pretty neat. Yes? Oh, absolutely. That's, I mean, so so when Colin was talking about the notion of accounts and then when you want to share something, he said 2 words, services and streams. Stream is an event stream. It's a published thing. Things are going out. I don't know who's out there who wants to see them, but if you want to, great. Services are, you're going to send me a request, I'm going to send you a response, an RPC, request reply. And those are the 2 major patterns. Because even load balance queues or the distributed queuing technology is still a request reply. It's just we automatically can load balance without additional sidecars or load balancers or any other goofy tech. So, any others? Yes.
You integrate with Kubernetes, as I understand, Kubernetes operator. Is it smart enough to, or the rules built in, I can say, I want to, here's the queue, I want to load balance, and also want to auto scale it, Kubernetes auto scale it, or is that something that's kind of like, you don't deal with that, and I have to do it myself?
So the question is, does the Kubernetes operator deal in such a way that the NAT system and them are talking about scaling? Is that fair? So Wally's the one that designed the operator. Do you want to take it? Or just say no? So the closed loop stuff on load balancing is an interesting problem. The information is there, and in the tech that we're coming up with, the ability to not have to ask for information out of the system, but it'll actually push it to you, is being introduced. And this was an idea that Colin and others on the team had. And now that we have accounts, we feel that we're in a perfect space because we can put that in a system account. And then the system account has to say, I will export this to you. Otherwise, you can never see that it's saying, hey, somebody's listening on Foo, or I'm using this much memory. But now all of a sudden, that's all going around. So I would imagine, and Wally will hit me with his book if I'm wrong, we'll start taking advantage of that in the operator sometime in 19, such that if you wanted to and you told it, hey, listen to this stuff, and here's the thresholds or whatever model you want, and you can auto scale based on that, that's a lot more possible now, I think. Is that fair?
So,
Yes.
to piggyback off of this question, is that information exposed via like the Prometheus operator? If I knew what topics I'm listening on and I wanted to set up like a horizontal pod autoscaler to listen for throughput or whatever, is that possible?
So the question is, on the operator, can you do throughput monitoring, things like that? Well, yeah, so NATS is designed in a way that was very specific to decisions that I made that I regret in the early 90s. I designed a pub sub system with a bunch of guys at Technicron, which became TIBCO, and everything was pub sub except for your reply, right? So I'd send the message out, and then there was a special thing underneath the covers called an inbox. And matter of fact, all of our special things are named under bar inbox. But in Rendezvous, they were special, meaning if you came along and said, show me everything, you'd see everything except the response. NATS is not like that. It is pure pub sub, meaning if you want to and you're allowed to, you're authorized, which by default you are, you can say, show me everything. I want to see all the requests going to them. I want to see the responses. I can measure latency, which is kind of what Colin was showing in that graph. You can easily say, I see the latency and I don't like it. And I'm going to press a button to say, start more of these. That's really, really straightforward with NATS. And then I think your other question was about monitoring. The original design of NATS, I took a lesson from Google, and it has the ability to have VAR-Zs and stuff, which are HD JSON endpoints. The system that's on master now that we're cutting release can optionally be configured with a system account. And as soon as you do that, the system wakes up and it starts sending messages, pure NATS messages out on all the stuff it's doing internally. And then if you want to, you can subscribe to those. Either you can service import them or stream import them. Or I wouldn't recommend it, but you can give yourself a user on the system account and directly look at them. But I like the separation, to be honest with you. Any others? Yes. So the question is, do you have a timestamp on the message and that synchronized? The answer is no, and the payloads are opaque to us. But that being said, in the last thing that we've been working on, we wanted to be able to coordinate, as well. And so what we've done is that we, instead of doing time, we do sequence based on event streams. And so if all of a sudden I get something out of order, I know I can ignore the one that was delivered out of order. So it's not as, it's not like a vector clock type of thing, but it's a simple mechanism that we can say, oh, okay, the message I just got from him, and then you sent me one, yours was older, I'll just, if it's an idempotent feed, which we always do. So all of our eventing out of there is always idempotent, meaning you have everything you need to know with the message in hand, and then we just added the sequence number so you know to ignore ones that come in, which in very large topologies like we're doing with NGS is possible, right? Because you're going all over the world and stuff. Time coordination is a hard problem, but it's an interesting one because if you can coordinate, it gives you a lot of things. And Google kind of taught everyone, again, like they have been, to think outside the box. And they go, well, wait a minute, if we actually just buy this fancy piece of hardware and stick it on our data centers, we know that all of the clocks, I think, will be within 2 milliseconds or something, 7. So that's their spanner window, right? For if there's conflicts, if it's in that 7 millisecond window, they got to kind of figure stuff out. Otherwise, they're good to go. But most people don't have that. So, any others? These are good questions, by the way. Thank you. Okay. Thank you guys very much. I appreciate it.